Okay, so we're talking about the gradient operator. It's the partial, a vector of the partials, the operations of the partials. So when we do that, we put that operation on a real valued multivariable function. That's the gradient. When we put that operation, when we cross it with a vector valued function, that's the curl. And when we dot it with a vector valued function, that's the divergence. And so the gradient, this gradient operator is essentially the derivative. It's the derivative of a vector value, of a real valued function. The gradient field is like the derivative. It's like rate of change of a surface, right? It's like direction and magnitude of rate of change. Curl is rotational rate of change of a vector field, and divergence is expansion rate of change of a vector field. Okay, and then we talked about these different fundamental theorems. We said an important part of the fundamental theorem is that you accumulate bits using the rate of change, right? And so we have for each one of these rates of change has its fundamental theorem. So which fundamental theorem uses the gradient rate of change? Fundamental theorem of line integrals, right? So here's the rate of change, right? The rate of change of f. So now we're gonna accumulate little changes of the vector field along C in the direction of C using the rate of change of f, using the gradient. And what does that equal? That equals the net change at the boundary, which the boundary would be like the endpoints of that curve, right? Okay, and so then there's a fundamental theorem that accumulates little bits of change using the curl rate of change. Which one was that?
Stokes Theorem.
Stokes Theorem. Right? So accumulating the curl and then looking at those vectors as the flux through your surface, getting the whole flux through your surface of the curl vectors equals what? Equals the net change around the boundary, right? Equals the line integral around C. And then we had a fundamental theorem that accumulated little changes using expansion rate of change. Which one was that? Divergence theorem. So here, you're accumulating what? Little amounts of divergence all throughout your solid. And if you accumulate all those, then it's the same as what the flux out of the surface, that's the shell of that solid. So these are our fundamental theorems of calculus. So there's this grand pattern to this whole thing in vector calculus. Kind of the key to it is this operator that's the derivative, right? It's like taking the derivative of a real valued vector value function, and then that derivative or that rate of change is used in the fundamental theorem of line integrals. Taking the rotational rate of change of a vector field is the curl, and then that rate of change is used in Stokes Theorem. And then taking the expansion rate of change of a vector field, and that rate of change is used to generate the little expansion of the little bits of your solid in your divergence theorem. And accumulating all those bits is always equal to, and every fundamental theorem is equal to what? Like the net change on the boundary of whatever thing you have, right? If it's a curve, then the boundary is the endpoints. If it's a surface, then the boundary is the thing, and then the circulation around the edge. And then if it's a solid, then your boundary is the closed surface. So there's all this parallelism and all this stuff. It's better than you think. I hope the enthusiasm, you can hear the enthusiasm in my voice. This is so cool, right? This is so cool. Any questions? Yeah.
Okay, for the second part, the on the other side of the equal sign of the curl thing.
This over here? Oh, this over here.
Yeah, that. Would that be like the same thing that you could do for the thing up top where f of b minus f of a?
Yeah, so yeah, there's all this part, right. So the right side of all of these are the net change for the boundary. The net change evaluated at the boundary. So the boundary of a curve is the endpoints. The boundary of a surface S in R3 is that edge loop, C, right? And the boundary of a solid E in R3 is this outer shell, the surface, the closed surface. So yeah, there's all this parallelism, right? For all of it. The left sides are all parallel, and the right sides are all parallel idea. Okay, what if you had Stokes theorem in R2? So in R2, what does the curl become in R2? So if you have curl in R2, which direction does it point? Yeah, in or out of the plane, right? So it only has a z component. So in R2, the curl is what? The curl is 0, 0, qx minus py. Right? So then what does this become? This becomes the double integral over your region of qx minus py dA in the xy plane. Green's theorem, right? Green's theorem, and it's also equal to this, right? It's just equal now to the circulation in R2. So Green's theorem is simply a special case of Stokes theorem where it just lives in the xy plane. What's that? Who was first, Stoke or Green, right? I would guess, I don't know. That's a good history question. My guess is that Stokes theorem was first. I don't know. Who knows? Okay, so and then we talked about there was that one web work problem that was like the R2 version of the divergence theorem, right? We talked about that last time. So it's the same. It's the same thing. It's like then the surface becomes that curve, and you're talking about the divergence in the region inside is equal to the flux, the one-dimensional flux out of the boundary. Okay, so that doesn't have I don't know if that has a name. The Green's theorem has a name as the special case of Stokes, but there does exist this special case of the divergence theorem, which is it's like the Green's theorem of divergence theorem. And so that problem, we talked about that problem in web work last time. All right. Questions on this summary of vector calc? Yes, please.
What happens if you take the divergence of the curl?
Okay, good question. So could you take the divergence of the curl, right? Because the curl is another vector field. So what happens if you take the divergence of the curl? Well, if the curl, divergence of the curl, yeah, I know there's something very profound here, but you caught me off guard. No, it's a really important question. I just yeah, off the top of my head, I can't speak to it. But so the curl is yes. So this just brings the question: is that a valid calculation? So in all these things, you have to know what they are. So for instance, this is a vector field. This is a multivariable real valued function. Okay? Can you do, say, this? Is that valid?
No.
Right. So first of all, is the curl of f valid, right? So yes. And what is that? When you do the curl of f, what do you get? Do you get a vector function or do you get a real valued function? That's a vector function. So is the divergence of the curl a valid thing? Is the divergence of the gradient of f a valid thing?
Yeah.
Yes or no? Is this a vector? Is this, what kind of function is that? It's a vector function. You can take the divergence of a vector function. Yeah. Okay. So those are important questions because it really forces you to know what is f, what is little f, what is vector field f, and what's possible. But the meaning of this, off the top of my head, I don't remember. But it is important. Just wasn't ready to talk about that. So no, it's okay. It's a good, very fair question. Okay, so what about the curl of that? Is it valid? Anything you could say about that? So what kind of field is this? That's a gradient field, right? That's a gradient field. And what are gradient fields? Conservative. And if they're conservative, then they're irrotational. So what about the curl of the gradient? 0. You see that? Yeah.
Actually, a similar question.
Yeah.
I wanted to the gradient of the divergence.
Gradient of the divergence. So is it valid? So what kind of thing do you get when you do this? You get a real valued function of x, y, and z. So could you take the gradient of it? You could, right? Okay, this is a function. This is like a function of x, y, and z, a real valued function. So yes, you could take the gradient of that. Gradient of the divergence. Yep, that's possible too. Okay, don't have enough time to. Yeah.
Is it the first fundamental theorem just for conservative fields? Is it for the memory roll right now?
For this now?
Yeah, for that one.
So this is gradient. So that's a gradient field.
Okay.
So you're right. That has, yes. If it's a conservative vector field, then it's a gradient field, and you can only do it because you need the potential function of that gradient field. So you're right. That's right. Other questions? Okay, so I have an example that brings together lots of this stuff. It's not that. It's this. Okay, so here is a vector field of water flow at the bathtub near a drain. There's the drain. Okay, so this vector field is this bad boy here. And it gives us the, so let me write it out horizontally. So it is, I don't need to write it out. This is just the x component, y, it's just vertical. You can read that just as well as you can read it horizontally, right? So this is the x component of the vector field. This is the y component. And this is the z component. And then I have the unit disk in the xy plane is the surface of the drain. So here we go. Okay, and so then there's going to be the disk, which is actually just like, it's like it's where the water goes through, but there's nothing there, right? So it's just the it's like a surface of air, right? It's a disk where nothing's there. So you're gonna, and then there's a strainer. that sits down in the drain, and we want to find we're going to eventually find the flux through that. So that's the unit bottom half of the unit sphere, centered at the origin. And so that's like if you stuck a strainer in the drain, and so then want to calculate the flux through that. Well, we'll go back to the first one. So there's both of them. So you want to find the flow rate of the water through the drain. So that vector field, this is in centimeters per second. So at any given point in that vector field, it's the flow. How are we going to do this? What are our options?
It's an open surface, so we can use Stokes theorem.
We use Stokes theorem?
We need a surface integral the whole thing, but that's not a good idea.
Okay, can we use Stokes theorem? It's asking for the flow rate. So that's the flux of this vector field or the curl of this vector field?
The curl. No, the flow rate is
It's asking for the flow rate of this vector field, the flux of this vector field through that. So can you use Stokes? You can't use Stokes because Stokes is for the curl of a vector field, right? Stokes would be the surface integral of the curl of something. We want the flux of the thing we're given. So we can't use Stokes. Does that make sense that we can't use Stokes? So what are we going to do? We got to do it. Our only option here is to do it directly. So, but it's not as bad as you think because of the surface. So you're going to see that when you parameterize the surface and do the flux, things are going to fall out pretty easily. So you got to do it directly. Does that make sense? So you can't use Stokes theorem. Understand why? Make sure you understand why. Anyone got an answer yet?
Yes.
What did you get? It's not 2 pi. Just pi. So it depends. So it depends how you orient, right? So if positive orientation is upward for that thing, then you should get negative pi. If you call the positive orientation up. No?
No, not.
Not weight.
Not weight. Just I'm thinking to myself.
Okay, sure. That's always allowed.
Yeah.
Okay, so 2, you have to be a little bit ingenious on number 2. 2 requires some ingenuity to avoid a nightmare.
It's not that.
Okay, quick. We got 5 minutes. So, anyone figure out how to do number 2 without doing the surface integral through that sphere, which is going to be nasty with that vector field? You guys figured it out? You guys figured it out?
I thought, but I didn't figure it out.
Okay. What do you guys think? What's that? They want to do the divergence theorem. So so tell me.
It's a closed surface if you add the cap.
Okay, so let's.
The bottom of the sphere and then the disk.
Okay, so that you put them together and it makes a closed surface, right? And so what happens when you took the divergence of F? What'd you get?
We got
It's really gross.
No, I don't think so.
No, it's not really gross, guys.
When we found X and Y.
All you need is the derivative with respect to x. That's not gross. And the derivative with respect to y. That's not gross. Now that's just, you just need to do a chain rule for that. What's the derivative with respect to x here? So the divergence is, this isn't bad, guys. Divergence is negative z. Negative z over that thing squared. And this is? I think it's the same thing again. Negative z over that thing squared, right? And what happens is the derivative of this with respect to z ends up being positive 2z over that thing squared. So if you do the chain rule, it'll be negative 2 times that over that. Maybe I put this in wrong. Maybe this is not supposed to be squared. I think that's got to be it. It's not supposed to be squared. Sorry. That's got to be the right. That's got to be what's going on here. So if that's just to the first power, doesn't really. So it looks like the water's a little bit more downhill now, but it doesn't matter. So I think it's supposed to be, if you have, yes, this is right now. Is it positive 2z now over that thing squared? Which is?
0.
Divergence is 0. And how does that help? Because now?
Isn't it just negative now, actually?
What?
It's just negative 2z now.
So
Because it's negative 1.
you got it? Yeah. So the divergence says that. So the divergence theorem says that equals the flux through S of what? F dot ds. And what does that surface consist of now? Hemisphere and a disk. So we've got S1 and S2. We know one of those is, so if this is the disk that we already did, it equals to?
Now it's negative. Oh, that was pi.
Right, so it's outward, we're going to do outward orientation. We're going to do outward orientation, then the one we did becomes positive pi, right? Everyone see that? No, negative, still negative if it's outward. We're still going, it's still going in there, so it's still negative. So therefore, the one that was asked for is positive pi. Right, did you catch it? So now in the divergence theorem for S, you have either going to be either positive as outward orientation or positive as inward orientation. Okay, so we'll just say outward, right? If it's outward as positive, then what we did before is still negative pi because the net flow in through that thing is still negative according to outward orientation, right? Therefore, this one for outward orientation has to be pi, which makes sense because the water's flowing out of the hemisphere. Okay, so there's some more cool stuff to this problem, but we don't have time. But this was, I think there's some valuable stuff in there anyway. The other questions related to another vector field, which we didn't get to. Questions on this? Does it make sense? Okay, remember, web work's due tonight at midnight, written homework due at the final. Study, study, study as much as you can before study session noon on Monday. Hope to see all of you there.